Please join me in here. All right. Do I got everybody? Okay, so this is a chapter you're going to be going, yeah, I've seen this stuff before. On the nice hand, we're not going to be doing a bunch of ice tables. Everybody happy about that? Okay, me too. That stuff gets really boring. Okay, so this is proton transfer reactions. We're going to have an introduction to mechanisms, equilibria, free energy diagrams, and charge stability. So a mechanism, this can be used to illustrate how a reaction takes place. It helps us understand why a reaction takes place. Ultimately, we can use this to make predictions about stuff we haven't seen before and design new reactions that we've never done before. Okay. So for every new reaction in the book, we're going to focus on its mechanisms. And this is going to be most of what organic chemistry is going to be from now on. Okay. Now, one of the things I want to point out before we get into mechanisms, this is the place that you're going to be very tempted to try to just memorize every individual mechanism every time you see it. Okay? I promise you, you'll have some sort of temptation for that. It's what, like 80-90% of students in organic chemistry try to do at first. And it is the way to just overwhelm yourself and have a terrible time. Okay? What I want you to do is focus on understanding why it takes place. Okay? Why does that mechanism take place? There's actually not that much to memorize in this course. The bigger thing is if you understand why the mechanisms take place, then when you see something new with something similar in it, you can figure that out. And you don't have to have the perfectly same thing every time, or else you get thrown off. Okay? Okay, so mechanisms are going to simplify organic chemistry. It doesn't seem like it at first, but that's because you're, again, going to be tempted to try to memorize them, in which case it doesn't simplify it, does it? Yeah. You got to use them as understanding why the pathway takes place. If you look down any situation where there's a hill in front of you, what do you say? Do you say that each of the hills are different, or do you say, hey, I can roll down that with a wheeled barrow? The second, right? All the hills are not different. Okay? Okay, so most reactions are going to be constructed from the same sets of elementary steps, which we can use over and over and over. I'm going to basically be giving you a bag of tools that you can then use these tools to construct all sorts of things, from LSD to, well, it is actually a legitimate drug now. They do use that to actually cure PTSD, which is pretty amazing. To, well, really whatever you want to make. Okay? Hopefully not something you'll get in trouble for. All right. And by the way, I did mention that if you make meth, I'm going to be incredibly disappointed in you and not acknowledge you as one of my students, purely from the artistry standpoint. Okay. Okay. Yeah, it's ridiculously easy to make. It takes no skill. And there really isn't a higher level for it. And it's just a stupid thing to make, even if you're trying to make money. I mean, just dumb. Don't do that. Make something interesting. If you're gonna get in trouble, do something interesting. Come on. Okay, so proton transfer reaction, or a Bronsted-Lowry acid-base reaction. Does everybody remember Bronsted-Lowry? Okay. Okay. So a Bronsted-Lowry base reacts with a Bronsted-Lowry acid. Okay. So the Bronsted-Lowry base is going to accept a proton. Bronsted-Lowry acids, on the other hand, donate protons. And that's the definition of the Bronsted-Lowry acid and base reactions. Base always accepts a proton. Acid always donates a proton. Okay? If you're a strong Bronsted-Lowry acid, what do? You always lose your protons, right? If you're a strong Bronsted-Lowry base, what do? So always accept a proton. If something is a weak base, what does that mean about its acidity? Yeah, it's a stronger acid, right? Okay, the weaker the base, the stronger the acid, right? The stronger the acidity, the weaker the basicity, right? Okay. Okay. Does everybody remember conjugate acids, conjugate bases? So a base always goes to a conjugate acid because it gained a proton, right? It now has a proton it could theoretically lose. An acid is always going to go to its conjugate base because it always is going to be losing a proton. There used to be a proton there, so it can take a proton on, can it? Okay. So proton transfer reactions, this are going to consist of a single elementary step where we transfer the proton. All of the changes that occur in the reaction at the molecular level are going to do so simultaneously. This is what we refer to as concerted, that they're all happening at the same time. Okay? And so you always have to represent that with a single step because they're all happening at the same time, right? You can't break it in to multiple portions. So again, what's going to happen in these reactions is we're always going to break the bond between the hydrogen and whatever its conjugate base is. This is then going to form a new bond with the original base, forming the conjugate acid. Now there is a curved arrow notation. The curved arrow is going to represent the movement of valence electrons. We don't represent the movement of atoms. What weighs more, atoms or electrons? Yeah. Yeah, the electrons move because they weigh far, far less, right? They're a lot less energy to move. The atoms, on the other hand, don't move. That's not what we're going to be moving around because those weigh far, far more. It'd take a lot more time to do that, right? Okay. So each of the double-barbed arrows is going to represent the movement of two valence electrons. This double-barbed arrow, everybody sees that double barb, right? That's moving two electrons. The curved arrow that originates from the center of a bond represents the breaking of that bond. It represents we're moving the electrons out of the bond. Okay? The curved arrow that points to an atom is going to represent the formation of a new bond. For example, right there. Everybody can see that one, right? We're forming a new bond to that hydrogen right there. The formation of a new lone pair of electrons can also be represented, which is this one right here, where we're moving the electrons from the bond onto the chlorine alone, right? And so that ends up with a new lone pair of electrons. If we want to represent one electron being moved, what would we do? One barb. You got it. Okay. Let's go ahead and stop here since I'm actually a little over time. And you all have a wonderful day. Okay.